on the central limit theorem. So this is the fourth lesson in the chapter. Technically this is the third lesson in the textbook, but I included an extra lesson in the series, so therefore this is lesson 4. So for this lesson we want to be able to use what we call the central limit theorem to solve problems involving the sample mean, assuming that we have a large enough sample. So we'll talk about what the central limit theorem is and how to use it. In order to illustrate this principle, what we're going to do is we're going to start with an example. So let's say that you have a professor giving a quiz to a class of 4 students, and let's say the 4 students is the population, very small class, and they get the following results. They get a 2, 6, 4, and an 8. I believe it's a 10-point quiz. So we want to find the mean of the quiz scores. So that's pretty straightforward. And since this is the population, we will call this sigma, right? So, or I'm sorry, not sigma. We will call it mu. So we simply add the scores together and then divide by 4. And then we will get our result. So I'll quickly do it on the calculator. Okay, and then we should get 5 for our mean. Now we're going to find the standard deviation of the test scores. So remember, to find the standard deviation, the formula is square root sigma x minus mu squared over n. All right. If you're looking for the sample version, it's n minus 1, but for the population, it's going to be n. All right. So in order to do this, you're simply going to remember the sigma means to add. X is your test score, and mu is what we just found. N is how many results we have, so 4 students. So we're simply going to do the test score minus the mean, square it, plus the test score, the next test score, minus the mean, square it, then the next test score, minus the mean, square it, and so on. And then divide that result by 4. You can also do this on a calculator, now that I showed you how to calculate this on the scientific calculator. But you would get 2.236. Now we want to construct a histogram. So in other words, we want to do like the bar graph where it touches. So we want to do the frequency on the y-axis. And we want to do the score on the x-axis. Since we're only looking at, 2, 6, 4, 8, this is really simple. All you have to do is just write those test scores down. You don't really have to worry about the class boundaries because it's a real simple histogram. So here they all have a frequency of 1, since there's only 1, 2, 1, 6, 1, 4, and 1, 8. So you can go ahead and draw these the same height. Okay, and that's your histogram. So this is known as a uniform distribution. It's uniform because it's the same throughout the entire distribution, so the same value. So notice it doesn't even start out as a normal distribution, it just starts out as a uniform. So now what we want to do is we want to take these same exact test scores, these 4 test scores, and we want to put them in a raffle, if you, so to speak. So just if you were to put them in a raffle and randomly select 2 test scores, all right, so you select 1 test score, then you replace it, and then you select another test score. All right, so you're replacing the test score after you select the first one. And then if you were to do this randomly, then what are the different possibilities? Okay, well, You can choose a test score of 2 and then replace it and then choose a test score of 2. You can also choose a test score of 2, then 4, and so on. These are all the combinations. So what we want to do is, with all these combinations, we want to calculate the mean. All right, so 2 plus 2 divided by 2 is 2. 2 plus 4 divided by 2 is 3. 2 plus 6 divided by 2 is 4. This will give us 5, 3, 4, 5, 6, 4, 5, and so on. Okay, so now we calculated the means. So these are known as samples. So we took a sample of size 2. So the sample size here is 2. So sample size equals 2. So it's not a very big sample size. Normally you would want a bigger sample size, but our population is small, so therefore we don't have many options here. So then what happens if we were to graph this on a histogram? So first, in order to do that, we are going to do a frequency histogram, or a frequency chart, and then do the histogram. So we're going to construct a frequency distribution of the sample means. So like, how many 2s do we have? Well, if you look at here, we have, 1, 2, and that's about it. There's only 1, 2. So frequency here is 1. For 3 2s, how many means of 3 do we have? Well, we have 1 here, 2, and that's about it. We have 2 of them. All right, what about 4? 1, 2, 3. 5. 1, 2, 3, 4. All right, 6. 1, 2, 3. 7. 1, 2. And then we have 1, 8. So 2 7s and 1 8. So what we're going to do, we're going to actually, before we actually do the histogram, we're going to calculate the mean and standard deviation. So, all right, so we're going to calculate the mean first. So to do the mean, we're going to add up all the numbers. You can use this guy, or you can use the original. So we got 2 plus 3 plus 4 all the way to 8. All right, so 2 plus 3 all the way to 8. Add up all those numbers, and we had a total of 16 numbers, which is going to give us 5. So notice that this is the same exact average as it was for before. We call this the mean of the sample mean. So this is the mu x bar. Remember what we calculated here? We were doing the average of the x bars. So one result is that the mean of the x bars, that's the mean of these guys here, right, is going to be the same as the mean of the original data. So that's one interesting property, is that if you take a sample and then you average those samples and you do the average of those guys, then you're still going to get the original average. So very interesting property. Now let's look at the standard deviation. If you were to do the standard deviation of the x bars, right? So again, you got to do the square root, and then you're going to do the x value, which here is 2 for the first one, minus the mean squared, plus 3 minus the mean squared, and you keep doing this all the way to the last number, 8, minus the mean squared. And then you're going to divide by how many numbers you have, which is 16. And when you do this, you're not going to get the same number. Okay, so now let's calculate the standard deviation. This is the standard deviation of the sample mean. So we're going to do the same way we did before. We're going to use the x value, which, all the x values. Here is the x bar values because you're doing it for x bar. So you're going to use all the x bars. So you have 2, then you have to subtract it by the mean, which was 5 squared. The next x bar value, 3 minus 5 squared, all the way to the last one, 8 minus 5 squared. And you have to divide by 16 since we had 16 numbers. If you remember, if you go back to this guy, we had a total of 16 numbers. So these are the x bars. Okay, so now I'm going to take the square root of that, and we get our result. You would get about 1.581. So notice this is not the same number that we got before. So if you were to look at the one we got before, we had 2.236 last time. So it got smaller. So if you were to do the distribution of sample means, and find the standard deviation of that, you will always get a smaller number. How much smaller? Well, I'll do it on the side here. You would actually, the formula for that is it'll be smaller by the original standard deviation divided by the square root of your sample size. So in this case, our original standard deviation was 2.236 divided by a square root, and in this case, we had a sample size of 2. Why is our sample size 2? Because remember, we said that the sample size here is 2. We took 2 test scores at a time, and that's our n. Okay, so how much, so notice that this guy is actually smaller than our original standard deviation, which was 2.236. So in other words, every time you were to do the average of a sample, of a bunch of samples, and you were to actually calculate the standard deviation of those averages, you would always get a smaller number for the standard deviation. And there's actually a formula for that. So the pattern is that to find the standard deviation of the averages, you would take the original standard deviation of the regular x values, the very first one that we did, and you would divide it by the square root of the sample size. So in this case, this was 2.236. And then the sample size is actually 2, because if you recall, when we did the sample, we took 2 test scores at a time. So this is my n. So if you were to calculate this, you would actually get the same number. You would get about 1.581. So that another interesting property of the distribution of sample means. We call it the distribution of sample means because we're looking at sample means, x bar. X bar is a sample mean. So it gets smaller by this amount. So this is always going to be the case. So if you were to take a bunch of samples and then average those samples out, you would always get these properties. So let's show you how the graph is going to look like. All right, so we're going to graph frequency versus the sample mean. Okay, I'm going to go all the way up to 5 because that's my highest. The highest number that I have, or my frequency, is 4, so I should be covered. And then I'm going to include all of these x bars from 2 through 8. Okay, so for 2, I got a frequency of 1. For 3, I have a frequency of 2. 4, I have a frequency of 3. For 5, I have a frequency of 4. 6, I have a frequency of 3. 7 is 2. And 8 is 1. So notice that the shape of this histogram is actually bell-shaped. So it's bell-shaped or Gaussian. So notice the bell shape. So what that's telling us is if we were to do samples, even though the original data is not bell-shaped, if you were to take samples randomly of the data and average those numbers and then graph those numbers, you would get a curve that is bell-shaped. And this is actually known as a central limit theorem. Okay, so this curve that we just drew is called the sampling distribution of sample means. So that's this guy. So a sampling distribution of sample means is a distribution using the means computed from all possible random samples of a specific sample size taken from a population. If the samples are randomly selected with replacement, then the sample means will be somewhat different from the population mean. However, on average, they'll be equal to the population mean. So the sample means, on average, if you were to average the sample means, you would get the population mean. But if you were to just randomly select a sample, take an average, it's not going to be the same as the population mean. This is due to sampling error, which is the difference between the population measure and the sample measure. So like we said, the histogram that we drew is the sampling distribution of sample means. All right, so what are the properties of this guy? Well, we kind of already talked about it. We know that if we were to average all of these sample means, that will be the same as the population mean. So in other words, the mu of the x bars, the sample means, so the mean of the sample means is equal to the original mean, the population mean. The standard deviations we said will be smaller. That's what we found out earlier. So it'll be actually smaller than the standard deviation of the population. And it'll be equal to the population standard deviation divided by the square root of the sample size. So that's what we were saying earlier, that the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size. And then the shape of the distribution is given by the central limit theorem. So let's go ahead and discuss that. So the central limit theorem, so basically as the sample size n increases without limit, that's why it's called the limit here, meaning that as n gets bigger and bigger, so like in our example, we had a sample size of 2. If we were to do a sample size of 3, then a sample size of 4, etc., as we keep increasing that sample size, the shape of the distribution of the sample means taken with replacement will approach a normal distribution. And we saw this firsthand. We only did a sample size of 2, yet we had a really nice normal distribution when we graphed it. The mean of this new distribution will have a mean of mu and a standard deviation of sigma over square root of n. All right, and I just provided you with another graph of the distribution of sample means. Notice that since the standard deviation is the original standard deviation divided by square root of n, this means that the curve is skinnier because the standard deviation is smaller. So we have a skinnier, narrower curve. And that's because the sigma x bar is actually smaller. So there's less spread. All right. So now we're going to go ahead and look at these bullet points. So when the original variable is normally distributed, this should say distributed. The distribution of sample means will be distribution of sample means will be normally distributed. So when the original is normally distributed, then the distribution will automatically be normally distributed. That makes sense. So it remains the same. But when the original is not normally distributed, like in our example, it was uniform, but it wasn't normal. Then in that case, a sample size of 30 or larger is needed to use a normal distribution to approximate the distribution of sample means. In our case, we only had a sample size of 2, but remember that our population was really small. So in that case, it ended up working out nicely. However, most populations are not a sample size of 4. They're usually much larger populations. So in that case, you need a large sample size in order to be able to use a normal distribution. The larger the sample, the better the approximation. All right, so how do we use the central limit theorem? So what you want to do is generally you want to draw the bell curve, right? Just like we did before in the other problems. You want to do the same. So we are going to draw the normal curve. However, remember it's skinnier. So you're going to draw a skinnier bell curve. So if the original looked like that, then the skinnier one more like that. All right. So it's skinnier and narrower. It should be pretty obvious. If you look at this picture, that looks much skinnier than the normal bell curve. All right, so now we want to convert the x bar value. So we want to convert the mean value to a c value using this formula. Okay, so that's the main formula you're going to use. This is very similar to the other one. Remember that the formula in the other section was x minus mu over sigma? Well, the reason why it's a little different is because you're doing it for x bar now. See the x bar? You're doing it for x bar, which means that you're going to need to do that square root of n, because remember that sigma x bar is sigma over square root of n. So that's why you have that. Then you want to find the corresponding area using the normal distribution table.
20 and out.
Okay, so we're going to do this example. So now, remember the first thing you want to do is do the bell curve. However, you need to be able to calculate the sigma x bar, because that tells you how much you're being spread out on each side. So in this case, they tell us that the standard deviation is 3 hours. So we're going to divide that by, so it says if 20 children were randomly selected, so that's square root of 20. So that gives us 0.671. So instead of spacing by 3s, we're actually spacing by 0.671 on each side. So I'll show you. So if we were to draw the bell curve, so we have a skinny bell curve, and I'll try to draw that a little better. Okay, and in the middle, we know that the average of the sample means. How do we know we're dealing with the sample means? Well, because they're finding the probability that the mean is greater than 26.3. So they are looking for the probability that the mean, which is x bar, is greater than 26.3. They're not looking for the probability that the number of hours is greater. They're looking for the probability that the mean of the number of hours. So therefore, this is the distribution of sample means, x bar. We're graphing x bar, not x. So therefore, we're going to need to use the properties. So we know that the original mu is that the mu of the x bar is equal to the mean, which in this case is 25 hours of television per week. Instead of spacing by 3s, because the standard deviation is 3, we're going to space by 0.671. So we're going to do that on each side. So we have 25.671 26.342 and 27.013. So we got 1, 2, 3. All right, so those are our numbers. So again, like we said, it no longer spaces by 3 because it spaces by 0.671. So they're looking for that the mean is greater than 26.3. So that's greater than around here. Okay, so that's where the x bar is 26.3. Greater than means to the right, so we're shading to the right here. So we need to calculate the z value. So z equals 26.3 minus 25 over the standard deviation. We just calculated this, so we're just going to write out 0.671 because since we calculated this earlier. And you get 1.94 approximately. All right, so we can go ahead and find out what the area is by looking it up at the z-chart. So remember, we are looking for the probability that z is greater than 1.94. So in order to do that, we need to do 1 minus the probability that it's less than. If you were to look it up on the table, the 1.94, you get 0.9738. So then your answer is 0.0262. And that is a probability. So it's a very small probability that the mean of the number of hours they watch is greater than 26.3. All right, so looking at the next one. This one's saying the average time spent by construction workers is 7.93 hours. So that's the mu. We have the standard deviation is 0.8. So we got mu is 7.93, which we know is equal to the mu x bar. And then we have the regular standard deviation is 0.8 hours. We want the probability that an individual who works at that trade works fewer than 8 hours. So this is an x value. This is not an x bar. So because they said the probability that they work fewer than 8 hours. The way they would say it if it was x bar, they would say the probability that an individual has a mean value that is fewer than 8. Okay, they would say it something like that. But here they don't say anything like that. So we're good. We're just doing the regular stuff from the previous lesson, not from this lesson. Okay, so we are looking at x is fewer than 8. So we're going to calculate the normal. So in this case, we have the regular normal distribution. We don't have the skinny one at all. So we have 7.93, and we are spread out by 0.8. 1, 2, 3. 1, 2, 3. So this is going to give us 8.73 9.53 and 10.33. This is 7.13, 6.33, and 5.53. All right, I think I did that correctly. So those are our numbers, and we want less than 8. So 8 is around here. So we want less than. All right, so we're going to calculate the z is 8, 8 minus 7.93 divided by a standard deviation of 0.8. Okay. Our value is 0.09. So that's our value, 0.09. So now we want the probability that z is less than that, since we want fewer, which means we look it up on the table. And it is 0.5359, which makes sense since we have over 50% of the curve. Now let's switch up the problem. The same exact scenario, but now looking at if a sample of 40 construction workers is randomly selected. So this is our sample size, n. Find the probability that the mean, x bar, of the samples will be less than 8 hours. So we're looking at the mean is less than 8, no longer the x bar. All right, so therefore we're going to use the sampling distribution as sample means. So we're going to draw that. Okay, skinnier curve. And remember that the mu x bar is equal to the original mu. So it's still going to be 7.93 in the middle. However, the spacing is going to be different. So 1, 2, 3, 1, 2, 3. So we're going to go by, so we need to calculate the sigma x bar, which is equal to the original sigma, which is 0.8, divided by the square root of the sample size of 40. So let's calculate that number real quick. 0.8 divided by, okay, so we get 0.12, so 0.13, about 0.13. So we're going to add 0.193 to 7.93. So you get 8.06, 8.19, 8.32. Now we're going to take away. So you get 7.80, 7.67, and 7.54. All right. So notice the spacing is a lot different than it was before. So now we want to convert this to a z value, right? So z, so 8, x bar is 8 is around here. Oh, actually notice that 8 is actually closer. It's actually sort of halfway between these, because this is 7.9, that's 8.06, so it's probably closer around here. So that's 8, and we want less than, like we said before. However, the area, the probability should be different because it's a different shape of curve, right? This is skinnier, so it should be a different probability. So let's calculate it. So z equals x bar minus mu over sigma over square root of n. So z equals, we just calculated x bar, or we know what x bar is 8. Mu is, the mu x bar is mu, which is, what was it, 7.93. And then we calculated this, that was 0.13. So you get about 0.54, which is a different z-score than we had before. This is actually a bigger z-score. So that would change up our area. So that means our area is around 0.7088. So the probability that z is less than 0.54 is approximately 0.7088. All right. So notice that that's substantially larger than it was before. See how we're covering more of the curve here than we did here? And that's because the shape is skinnier and therefore we cover more of it. All right, so big difference between the answers. So I provided this example so that you can compare the differences between those two. All right, so last problem. We want to do the average age of a vehicle registered in the US, and they tell us that it's 8 years or 96 months. We're going to use months here since standard deviation is in months. So the average is 96. Standard deviation is 16. If a random sample of 36 vehicles is selected, so that's our sample size, find the probability that the mean of their age is between 90 and 100. So that means x bar is between 90 and 100. So that means that we're looking for 2 z-scores, 2 x bars. All right, so let's draw this out real quick. So we have the skinny bell curve, since we are looking at x bar. Okay, let me erase this because this is confusing with all the bar and with all these underlines. We're looking at x bar. All right, so this is the same thing as the mu of x bar, so that's going to be 96 here. This we need to calculate. So sigma x bar is 16 divided by square root of 36. So 16 over 4. Or I'm sorry, 16 over 6. Square root of 36 is 6. All right, so let's do that on the calculator real quick. You get 2.67. All right, so we're going by 2.67s here. So 98.67 so 101.34 and about 104.01. 93.33. 90.66 and about 88. All right, so we want it between 90 and 100. So 90 is around here, and 100 is around here. So we want this probability here. All right, so that means we need 2. This is x bar 1, and this is x bar 2. So we need to convert it to 2 z-scores. So we need to do z1 and then z2. So we're going to do x bar, the first one, minus mu over sigma x bar, which is 2.67. Now we're going to do the same thing for z2, 100 minus 96 over 2.67. So for the first one, we get about negative 2.25, and the other one, 1.50. So now we're going to look up, so remember to do the z-scores, right? Or to actually calculate the area between 2 z-values. We take the z-value for 1.50, and then we subtract it with the z-value for less than the other one. So we got to find both of those on the table. So the first one is 0.9332. The next one is 0.0122. So you do that, you get about 0.9210. All right, so that's your guy. So this is how you do these kind of problems. So again, be careful with x bar versus x, because it changes the shape, whether it's skinny shape, like here, or the regular one, which is just the normal shape, versus skinny. So just be careful with the wording, and you should be able to do fine and use the central limit theorem correctly. Hope this helped, guys. See you later.